I'm going to show get an example down and of a two-tailed test. And first of all, as you copy it down and as you read it, I want you to figure out in your head, why do you think this situation is slightly different to the ones we've experienced thus far? Good word, thus. Anyway, the producer of the TV show claims that it is politically biased, or unbiased, sorry. So it doesn't favour any of the three parties. It's like Newsnight, Question Time, or whatever. If this is the claim, if you take someone off the street, it is 50-50 whether he or she will say the program favours the government. Producer of a TV show claims that it is politically unbiased. They say that if you take someone off the street, it is 50-50 whether he or she will say the program favours the government. Okay? 50-50. Take someone random off the street, just random. Does this program, I mean Georgina, if I asked you, does Question Time support the government or not? You don't know, you don't care, you don't know the program, do you? Okay? But assuming that the person who's watched the program will be 50-50. So out of a group of 20 people, how many people would we say, how many people would we expect to say that the program supports the government if there was 20 people? 10, if it's 50-50. Okay? However, when 10 people selected at random are asked the question, does the program support the government or the opposition? 9 say it supports the government. It's quite a lot, isn't it? Test this claim at the producer's claim, that is, at 5% level. Okay? So there's the problem, there's the situation. The producer of a TV show claims that it's politically unbiased. If you take someone off the street, it's 50-50 whether he or she will support, say, the program follows the government, favours the government. However, when 10 people selected at random are asked the question, does the program support the government or the opposition? 9 say it supports the government. Test this claim at the 5% level. So let's get the theory part done first. Let's say, what are we going to make x? This is binomial distribution. What are we going to say x is? What does x represent, first of all? Theo? Yeah, so what's our success here? No. No. It's not a number. X could represent a number, but this part, we don't say x is a particular number. X is, Stephen? No, I said, do not give it a number. Curtis? X is the government. What does that mean? Got me? Yeah, the number of people. That's the key bit, number of. people who support the government. I know what you were saying there, Curtis. But it needs to be... Right, now to set it up, we look at the theory behind it. What is the producer saying the theory should be? What is the probability of someone saying that the programme supports the government? Theo? No, we're looking for a number now. Stephen? 0.5. Probability of someone saying the programme supports the government is 0.5. And therefore Q is also equal to 0.5. What's N in this example? The sample size. Tom? 10. Sample size of 10. So X is modelled by a binomial distribution. Binomial distribution 10 and 0.5. Okay, so there's our binomial distribution. Now let's set up the test. We have H0 is what? What is what we'd expect according to the producer? What would she say, Max?
Well, that 50% said that it's biased and 50% said it's unbiased.
So P is
0.5.
yeah, good. 0.5 there corresponds to H0. P is equal to 0.5. Now, H1. Can anybody tell me what is the difference with the H1 now? Look at the question. Are they saying that the probability is bigger than H 0.5, or is it less? In question, is there any wording which suggests that it's larger than 0.5 or less than 0.5? Tom, what are you saying?
It can be either, as long as it isn't 0.5.
Yeah. Can anybody explain why Tom said it could be either? If you read the question, why is that, Louis?
Because we're trying to test whether it's like 50-50, so if it's not 50-50, then his claim is wrong.
Yeah. We're not worried about whether it's more likely to, someone is more likely to say that it favours the government. We're not worried about whether it's particularly saying whether it's less likely for someone to say they support the government. As Tom said, the point being here, we're testing to see if it is 0.5 or not. It could be larger than 0.5, it could be less than 0.5. Okay? We don't care, it's either or. So, this is an example of what we mean by a two-tailed test. Because H1 now is not equal to 0.5. We're not testing whether it's bigger or less than, we're testing whether it's not equal to 0.5. And the significance level is 5%. But because the not equal tells us this is a two-tailed test, so two-tail, this means that although we've got a significance level of 5%, we actually have a significance level of 2.5% for each tail. I'm going to explain that a bit more in a second. Because it's a two-tailed test, our significance level effectively gets halved. Now, we've got issues here. What actually happened? 9 of them got selected out of the 10. So we've got to calculate a probability involving 9. Now, what was our test before? How did we know its probability to calculate before? What was our little thing before, Curtis? Yeah. By looking at what was here, if it was greater than, we'd work out greater than or equal. If it was less than, we'd work out less than or equal. So what do we work out? Probability of not equaling 9? No, we don't. Theo, what do you reckon?
Would you probably greater than 9, probably less than 9, less than equal to 1, greater than equal to 1?
If it was less than or equal to 9 and greater than equal to 9, it would equal 1 plus the probability of x equaling 9. You'd end up with a probability greater than 1 there. Not a bad idea. It makes sense, doesn't it? If it's not equal, it makes sense to work out less than or equal to 9 and the probability of larger than equal to 9. But the thing is, we know all the probabilities are going to add up to 1. And we're replicating because it's equal to 9, this is just going to equal 1 plus the probability of x equaling 9. We're not, that isn't the way forward there. Any ideas? Well, first of all, what's the expectation? How many would we expect? And sample of 10, how many would we expect? If P is 0.5, how many would we expect to say the program favours the government, Stephen? 5. The expectation, which is n multiplied by P, 10 times 0.5, is 5. So what happened here? How many people did it? 9 people. 9 is more than we expected. We would have expected, yeah? So therefore, we have to calculate the probability of x being larger or equal to 9, because what actually happened was more than what we expected. Okay? Then it's a case of we can calculate this as 1 minus what? Less than or equal to 8. And we can get this probability from the tables, which you can perhaps hear me where the microphone is. N is 10. So n is 10, p is a half, and less than or equal to 8, 0.9893. Which equals 0.01. Sorry?
It's like greater than or equal to 100 is greater than that.
Oh, sorry, that isn't equal.
Well, it's 100 something.
Yep.
Less than or equal to 9. It's greater.
Don't worry, which equals that. Okay? So the probability of x being larger or equal to 9 is equal to that. Now, because we said it was a two-tailed test because of this not equal to, it means that the significance level gets halved. The significance level gets halved. So we have to compare this to 0.0106. Now this is smaller than 0.025, which is 2.5%. Okay? Therefore, what is our conclusion? Which hypothesis do we accept? Yes. Yes. This probability is too small to have happened by chance. 9 out of 10. That's clearly too small to have happened by chance. Except H1, which means there's evidence to suggest that the producer's claim is inaccurate. Leave it like that.
Wouldn't it be 0.107?
Am I?
Yeah.
Yeah, that would be 0.1. Sorry. Doesn't change the result of that. Yeah. Doesn't change the result of the test, but yeah. Okay. Now, if we examine what happens here, let's examine why we split the significance level in half. Now, I'm going to draw a quick little bar graph here. Here's the probability that x equals a certain value. You're better off, Maria, going on a computer and going on YouTube in about 10 minutes and watching this video and going from there. That'll be my little thing for you. Yeah, okay. Now, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay, now n is 10 here. Now if I was going to draw a cheeky little line graph, well not line graph, cheeky little bar chart, the most probable value will be 5. In this, because n is 10, p is 0.5, the most probable value would be 5. You agree? Now, in this case, it's going to be symmetrical because the probabilities are equal. Probability of success is 0.5, probability of failure is 0.5. But they're going to be less likely like this. Okay, so I don't know what the exact numbers are, but whatever. Now, what we have here is that we had an extreme case. In this case, we had 9 of them. We worked out the probability of at least 9, okay, which was this part here. Now, this is what we call the upper tail. It's unlikely that 9 and 10 are going to happen. They're some of the most unlikely values to happen. This is the upper tail, okay? The least likely ones are going to be here. Same probabilities, but, just on the other end. These are what we call the lower tail, okay? Now, because our H1 said that P was not equal to 0.5, it meant that if we'd have done the experiment, we weren't sure whether we'd get really extreme lower values, that's the lower tail, or really extreme upper values in the upper tail. We weren't sure because P was not equal to 0.5. We weren't sure either way which was going to happen. Therefore, the significance level, which we said was 5%, has to be split in two. We'll have to allow for 2.5% in the lower tail and 2.5% in the upper tail. Okay, because we're not too sure whether it's going to be lower tail or upper tail. With our ones previous to that, ones which we did last week, we had an H1 is P is larger than 0.5, for example. Okay, and then we're saying that we're expecting it on the upper tail. Therefore, all of our significance level can go on the upper tail, the upper extreme. Okay, but here, because we've got a not equal to, it could be lower tail or upper tail, and we have to split our significance level to counter this. Okay, I hope that's kind of made sense. The key is interpreting this from the question. Now, some exams, they will not have this two-tail test. Sometimes they'll just have a normal test, what we did last week. You've just got to be a bit wise to it. In the question, if it doesn't mention anything about it being more likely or less likely, you're going to assume it's two-tail. Okay, they're the key words to look for. Things like more likely, less likely, proportion increases, proportion decreases. Words, if you see words like this, you're thinking this is fine. This is just a one-tail test. It's just as normal. If you're not seeing things like this, then you're thinking, this is two-tail. Okay? Any questions with